AI and a lot of topics that are relevant for socially impactful settings such as conservation and public health most broadly. Carl is our third speaker for the semester. We have a lineup of many others leading up until the end of April. So please check those out if you haven't already seen them. And to introduce people, CRCS is directed by Professor Milan Tambe, who is currently in India and may not be able to join. But Kai Wang and I are the organizers for the semester. We're both PhD students here at Harvard, advised by Milland. And then we also have Hyla Bernstein, who is the program administrator of CRCS. So without further ado, let me introduce Carl. So Carl Boettiger is an assistant professor in the Department of Environmental Science, Policy, and Management at UC Berkeley. He works on problems in ecological forecasting and decision-making under uncertainty, with applications for global change, conservation, and natural resource management. He is particularly interested in how we can predict or manage ecological systems that may experience regime shifts, sudden and dramatic changes that challenge both our models and available data. His approach blends ecological theory with a synthesis of heterogeneous data and the development of software, a combination now recognized as data science. So with that, I'll turn it over to Carl. And I also say quickly two things. One is that this is being live streamed on YouTube and the recording will be made available afterwards. And then two, Carl welcomes questions throughout. So please feel free to put questions in the chat or raise your hand and we'll monitor those and funnel them to Carl as appropriate. Now to you, Carl. Thank you.
Great. Thank you, Lily. So just shout out if you can't hear me or something seems funny with the audio or visual as we progress in our virtual world here. So thank you for the invitation. It's great to be with you all. I'll be talking about, well, algorithms save our planet. And will you regret it when they do? So I get to talk about the big questions, right? So climate change, increased forest fire risk, overfishing, transformation of agriculture, the devastation of ecosystems like the pine bark beetle devastation you see going here, destroying forests. And of course, environmental change can also drive human health changes, as we have all learned too well. So our polar bear sitting there is thinking what to do. Well, I'm going to give you the perspective of an ecologist. And ecology is an old field, perhaps the oldest of fields. Though the name goes back to sort of Ernest Haeckel in the 1800s, and same time that economics is really becoming a field, ecology is becoming a field, and it's kind of boring quantitative, dealing with the vast complexity of the biological world. And one of the early lessons that we have as sort of theoretical ecologists, hammer term for maybe 150 years now, is that even very simple processes make very complex dynamics, such as oscillatory dynamics, chaotic dynamics, sudden bifurcations and tipping points may even transition our whole ecosystem in some sudden transition. At the same time, we know that ecosystems are rarely simple. Simple models do complicated things. So how much more complex is it going to get when we try more realistic ecosystems? Ecosystems are full of biological complexity and stochasticity and other forms of uncertainty. So we have this vast array of problems. What are we going to do about them? How do we handle that? So first, I'm going to take kind of the classical approach that we have done within the past sort of 100 years in ecology of kind of thinking, how do we make decisions for these very complex problems? And we kind of first approximate the problem to what you might call, if you were an economist, a stylized model, and then find the optimal solution to approach that. And we will see how far that gets, and then we'll revisit that. So you can think of those as sequential decision processes. You have state action pairs. You observe your environment, you observe your ecosystem, you have to take action, then you get to observe it again and say, oh, maybe that was a bad action, I'll try something else. We're going to look at this first in the context of harvests, of fish. Fish stocks have been perhaps one of the longest running time series we have in ecology, and it has often been our crucible not only for a global problem of overharvesting that we want to confront, but also as a way of studying sort of this larger context of decision-making in a complex ecosystem. And so it's where perhaps the theory as well as the practice is most developed. I think many of the lessons that we see in managing fish apply to other areas of ecosystem management as well. So I'm going to go all the way back to the 1950s, where we get our first theory and what we call MSY, maximum sustainable yield, still governs how we do a lot of decision-making for harvesting fish today. Now, the basic idea is simple. So you imagine your population of fish obeys some growth curve. So if you have no fish, then you get no fish next year. If your fish population is sort of untouched, it grows up to some size where competition between the fish for resources mean that it's going to stay at that steady state, so no growth. Somewhere in between that rate, you get less competition. There's some sort of maximum growth rate. Great. That's what we knew about in the 1950s. We didn't know exactly the shape of this curve, and we still don't, but that there should be some kind of maximum somewhere in there. So if you think of this as a decision problem and you want to maximize the harvest of this resource, well, we can go back to basic theories of Bellman that use these natural resources examples in early work in establishing dynamic programming. It's the same answer we find within the fisheries literature. Simultaneously, both Gordon and Schaefer showed this in separate papers in 1954, but you want to get back to this biomass that we call at maximum sustainable yield, this maximum growth rate. If your fish are sitting around there, they're most productive, right? So you harvest down to that. Okay, so if you think of that in terms of a control rule, you can say, given I observe some population size, what should the number of fish I leave in the sea be, the biomass minus the harvest? And it says, well, if it's below that target, I should just let it grow. So the harvest is 0, or the escapement is whatever the current population is. And if it's above that level, then I should just bang it right back down to there. It took us another kind of 20 years to update from this rule of sort of just get there asymptotically to get there as quick as possible. And as we'll see, a good thing, most of our policies never actually changed from the sort of asymptotic control to that bang bang control of getting to BMSY. So that was a very simple model. I said ecology was complex, and then I gave you the sort of most trivial model I could. And we have been kind of chipping away at that ever since. It didn't take long after we came up with bang bang control on harvesting of fisheries that folks looked at that and said, well, blah, blah, that assumed that the system is completely deterministic, that you know the rule, that how it's going to grow exactly, you know the future population size exactly. So in 1979, Bill Reed took a look at this in mathematical terms and said, what if there is stochasticity, the population dynamics are uncertain, and was able to prove that, in fact, this didn't change anything at all. So if the growth is stochastic, it doesn't follow exactly that rule every year, you should do the exact same thing as if it weren't and just kind of harvest it back to where on average it reaches the biomass at sustainable yield. And you can prove that under that assumption in quite general cases. So you have put in the first kind of uncertainty, sort of uncertainty about the process. And so far it says uncertainty about the process isn't so important. Well, that's going to puzzle people for a long time. And we can zoom forward another decade and a half to Clark and Kirkwood looking at this problem. And they squint at Reed's analysis and they point this out. So I'll give you the quote. An important tacit assumption in Reed's analysis, as in other works that have done this, because this is mainstream here, is that the recruitment level is known exactly, right? And so in fact, the assumption of uncertainty didn't really do anything because you get to observe the system. You get to observe it exactly, and then you get to harvest. So there's really no risk in the model. And of course, the real world isn't like that. In the real world, we have actually great difficulty knowing exactly how many fish are in the sea. You can't exactly go to the sea and do a census. There's uncertainty there. And that combines, that's their intuition is saying, well, if you didn't know that, well, then maybe you wouldn't do the same thing in the stochastic case as the deterministic. Maybe uncertainty would make you more cautious. So does it? Well, Clark and Kirkwood decided to tackle that problem. They sat down at an early computer and made some calculations, came up with something that looks like this. And you can see uncertainty getting a bit bigger. And they found in these cases, there were many places where as uncertainty got large, you actually decided to harvest more. So remember this escapement kind of plot. Leaving fewer fish in the sea means that you're below this kind of flat constant escapement line. And they were saying, oh goodness, when we put both kinds of uncertainty in, we find a surprising result. Seems to contradict conventional wisdom, as they wrote in their own paper. But then being scientists, you learn that if we're scientists for long enough, you can stare at anything and kind of argue both sides. And they were able to kind of convince themselves that maybe this really did make sense, that you were supposed to contradict the conventional wisdom. And with two kinds of uncertainty, rather than seeing a more cautious policy, harvest less, you see a less cautious policy. Well, okay, that didn't really make everybody else all that confident. And researchers have continued to kind of scratch away at that. I'll jump forward again in history to work of Gautam Sethi and colleagues in 2005. They looked at that analysis and they said, well, you know, the math was kind of complicated and they took some shortcuts. in Clark and Kirkwood, and some of the later work, we're going to try again and put measurement uncertainty in a more realistic way. And oh dear, so they come across the same counterintuitive result, even more extreme. So this is the measurement uncertainty, this little line way down here that says leave fewer fish into the sea. And so they squinted at it and they said as well, it may seem counterintuitive that measurement error causes a lower expected escapement than you would in a deterministic fishery. But being good scientists, they squint at and argue that this maybe makes sense. They do note some caveats. They say that, well, in fact, we needed some shortcuts too because the math got really tough. And we specifically assume that our manager is using only the most recent measurement when forming expectations. That means literally the manager is doing this kind of Bayesian prior thing and saying, oh, this is my distribution over possible states. I know that my measurement isn't perfect, so I have a belief as to what the current state is, but I inform that only based on the most recent measurement, which, strictly shouldn't be true, right? And they say, we're doing that just because it got very, very complicated not to. Okay. Luckily, at the same time, we can kind of turn to a different set of literature. In particular, Smallwood and Sondic back in the 1970s discussed this particular kind of problem where the system is partially observed, which may be, as you know, it's not a Markov decision process, but a partially observed Markov decision process. And we're able to prove some very handy theorems about the state of the optimal solution for a partially observed Markov process, in particular that this payoff function has this piecewise linear convex behavior here. And this allowed an algorithmic approach to being able to find the optimal solution. Unfortunately, those algorithmic approaches still wouldn't scale very well to a problem as complicated as the fisheries case. And so we had to wait until about 2008 when we have the SARSOP algorithm is published over here, where we have an approximate POMDP solver based around that same theorems of Smallwood and Sondic, where we can solve the problem in the full complexity of the fisheries case, where we can get approximate but very close to what the optimal policy should be when we do exactly what Sethi warned us would be difficult, taking into account the full history. And so finally, when we do that, we learn that there isn't anymore a paradox. So in fact, if your past beliefs, so looking at all of those previous states, you can represent that knowledge as a belief over what the true stock size is. And if you really believe the stock size was very large, well, then indeed, you should go at least at some stock sizes and harvest more than the constant escapement. But if your past belief is the population size is much smaller, you should, in general, be much more conservative. And the larger the value of the observed stock size, the more conservative you want to be. So zooming back out, sort of what is the lesson there we see is that by being able to sort of not take the shortcuts and solve the problem of measurement uncertainty more exactly, we in fact discover something that's very intuitive, that your sort of fundamental intuition about the precautionary principle is true, and you can kind of see it embedded here. If you've seen lots and lots of low values or even sort of average size values, and then you observe some big number, you should probably think, oh, that's not something I've seen before. That's probably a measurement error, right? Conversely, if you happen to have seen very large values for a long period of time and you observe a very, very small stock, you can think, that's probably a measurement error on the other side, probably an underestimate of the true stock. I'm probably safe harvesting a little bit more. But overall, the greater the uncertainty, the more cautious that rule becomes, just as you would expect. So we have sort of confused ourselves for over 50 years by oversimplifying that problem. And as we are able to solve it more exactly, we can get a better understanding of what's going on. And that difference really matters. So you can take an example from projected fisheries policy up to 2050 in this paper appearing in PNAS. So they said, here's what we've done historically, slowly over-harvesting fish even since 1980. If we continue what we call business as usual for all stocks, this goes down both in the number of stocks that are overexploited and quickly destroys both the profits and the stocks themselves. But they say, should we follow the sort of the classic NDP solution? Now, being economists, they can do this clever trick. They call this rights-based fisheries management. So this policy is based on us doing sort of the constant escapement rule, instead of the way that we actually manage fisheries, which is this thing called MSY, where you say sort of asymptotically get there. Well, they say under rights-based fisheries management, you get there very quickly. Now, it's clever as an economist because they say that this prescription isn't prescribed, but rather it's sort of the description that it is the optimal thing, so it should be discovered by the market. So unfortunately, we can see that this bang solution is in fact the least is the least safe under a system where there is imperfect information. As you can imagine, taking a very rapid approach to what you think is the optimum may be great when you have perfect information. When you have uncertain information, it can go very badly. So here, with up to 20% measurement error, which is still potentially generous for our estimates of stock sizes in the sea and marine fish, you very quickly deplete the stocks even faster under a bang strategy than you would even under business as usual, which is kind of like an overly aggressive version of MSY. This MSY thing that says, oh, just asymptotically get to that size does a little bit better under uncertainty because it isn't so aggressive at the beginning, bang. But you can have a POM-DP solution here that looks for accounting for the uncertainty, and managing under that, you do indeed get this very large recovery that was still promised. And of course, as an economist, you would say, well, then that would have been the technique that would be kind of discovered by the invisible hand, so to speak. It would never, use something. The invisible hand would never use MDP if it wasn't the best thing to use. So this is good. We can allow the approach. To the sort of intuitive approach we can discover mathematically to also make a really big difference in overall fisheries outcomes. So we have slowly been able to build up our uncertainties. However, so far things have been very simple. The underlying models are very simple. We have process uncertainty, observation uncertainty, and by borrowing from some relatively recently designed algorithms like SARSAT from our colleagues over in the computer science and artificial intelligence realms, we have still been able to navigate our way through those uncertainties and come up with a policy that is sensible. Unfortunately, that's still predicated on us knowing, or more or less knowing, what the right model is. So we write down a model, we have to then estimate the model parameters, compare against other models, and say this is the underlying process. This invariably gets us into trouble. It gets us in trouble because of the models in ecosystems are always non-unique. It's impossible to validate a model when the observed data can correspond equally well to any of a number of possible outcomes. This was pointed out early on in this fantastic paper by Naomi Orskis and colleagues. The validation of numerical models of any natural system is impossible because they're open systems. And therefore, the primary value of a model is not predictive, but heuristic. So a model that can create accurate predictions can still lead to very poor decisions when it is not the true underlying model. Here's just a quick example of that in fisheries. Here I have two species, actually have an interacting species of bass and cormorant here. And here is one model that is predicting their future biomass and telling me how much I should harvest the target species of bass, as well as a herring species the bass feeds upon that I don't get to observe. And the cormorant is a species of conservation concern. It eats the same food, the herring, that the bass eats. But of course, we don't harvest the cormorant, we just try to restore it. And this model makes very accurate predictions, but the decisions that it's leading to are forcing the long-term decline of the species, both the bass and the cormorant. On the flip side, over here, we see a model that is making rather terrible predictions, way underestimating and way overestimating the cormorant and the bass, respectively. However, it is leading to rather decent decisions as far as the overall recovery of the species is concerned. So you can have accurate predictions, poor decisions, or you can have poor predictions and good decisions because models are not unique. A quick way to see that in our fisheries, a simple fisheries model, is if you consider these growth curves. If this true model has this kind of funny shape here, right? We know that the best thing to do is to harvest it like wherever that maximum is. So there's an infinite number of models that are not unique, but share that optimal harvest rate, right? Such as the silly blue curve, which is obviously over predicting the population size. And there are also an infinite number of models that can get quite close to this green curve in terms of absolute distance, but are just going to have the peak in the wrong spot, right? And so they can make much better predictions, but lead to a policy that's over harvesting, right? That's pulling the stock way down here instead of the size that it should be up here. So it's just one way in which the fact that models are not unique can lead us astray, and we don't know what the right model really is. So once again, we have our global problems. What do we do about them? So to borrow from Schindler and Hilborn here, a great deal of research to inform environmental conservation and management takes this predict and prescribe strategy, in which improving forecasts about the future states of an ecosystem is the primary goal. However, sufficiently thorough understanding of the ecosystems needed to reduce those deep uncertainties is probably not achievable. In other words, the model uncertainty we were just looking at. And they propose a different approach and actually point out that this different approach is no surprise to the people actually in charge of making most management decisions. Rather than think of a model as a predictive tool, researchers should integrate more closely with policy development to identify the range of alternative plausible features and develop strategies that are robust across all of the scenarios. So the goal is not to narrow down to this is the correct model, I've estimated the right model, but to broaden out that all of these scenarios could be possible and I can't really rule any of them out, but rather look for a policy that works across those. Well, how do we do that? So rather than look for an optimal solution to an approximate version of the problem, I'm going to kind of turn this on its head and say, are there more approximate solutions to the actual problems, right, that are robust across all of those possible versions of the actual problem? In conservation management, we call this scenario planning. And it's often done sort of non-numerically. You just kind of think up different ideas and you say, well, if any of these cases were true, do we have a strategy that would be robust to any of the scenarios? Sometimes we can generate that in simulations. Sometimes that's purely a heuristic exercise. Well, looking at ways to solve these more and more complex, partially observed Markov decision processes, we came across other developments in the artificial intelligence literature about model-free deep reinforcement learning that sound just like this. And just like this in that we no longer try to learn the underlying dynamics to make the prediction. Instead, the reinforcement learning agent, the artificial intelligence agent, is trying to learn a robust strategy it can use in whatever environment you toss it into. So in this setup of reinforcement learning, you have over here your agent. This can be an actual manager. This can be your artificial intelligence robot. And it interacts with an environment you can think of as a simulator. It takes an action, it gets back an observation and a reward. And it just plays that millions and millions of times, and we see what happens. So of course, reinforcement learning is much older than computing. You can see it in behavioral science and teaching this chicken, for instance, that it should peck only on the pink dot. And when it pecks the pink dot, it gets a reward. When it chooses a different dot, it does not get a reward. And the chicken doesn't need to be of any predictive power. It doesn't need to know what dot's going next. It just has a simple rule. I peck only on pink, and it learns really quickly under this positive reinforcement. And so we can train computers like this too. And so here is an algorithm from the 1990s attached to this little robot. This little robot is trying to learn to move in the direction of the arrow. And it has no prior knowledge of that goal. It's just kind of experimenting around. As you see, after about an hour of it experimenting around, it kind of discovers a mechanism by which it can kind of slowly move forward. It may not be the perfect mechanism, but it moves it in that direction. And this seems very kind of almost biological, the way this robot looks. It's a way of kind of discovering an inch forward strategy here. Now, these approaches have been very successful in the past couple of years. We've seen reinforcement learning power solutions to Atari games. This was sort of general learning there in which a single agent is able to play over hundreds of different games at above human performance, as well as exceeding human performance in other games that are classically difficult like Go and chess. And most recently in the past couple of weeks, we've seen reinforcement learning again show up on these glossy covers in playing StarCraft, in driving race cars at above the performance speed of the best F1 drivers in Sony simulations, and then even in the nuclear containment example 2 weeks ago, showing that AI can learn to control a magnetic enclosure for a nuclear fusion reaction in a simulator as well. So powerful, successful solutions out there. This is just one example from learning motion through this kind of trial and error approach, which you have maybe seen. And the important element that these examples highlight is that an agent is able to learn to perform in a variety of different environments. If it's trained against sort of enough scenarios, it can kind of learn what to do. And it learns what's to do in this constant feedback of there is a reward, in this case, a reward just for getting kind of as far as you can through this course as possible. And it iteratively learns through playing again and again and again what's the right strategy to sort of move those muscles. So it doesn't know any physics to begin with. It has to kind of learn all of that from the ground up. So, okay, reinforcement learning is successful in robots and games. What about saving the planet? So we decided we would attempt to apply this to our simple examples in fish. So we have built one of these so-called gyms following the OpenAI gym standard with a whole suite of different models on underlying simulations for fisheries dynamics. Again, starting with examples where we know what the right solution is, because when we know what the right solution is, we can compare and see if we are actually doing the optimal for this simple theory. Then we'll try more complicated models. So this was a leaderboard for some of the fisheries examples where we compare your score as a fraction of the constant escapement score. And with sort of vanilla settings, we show many of you sort of off-the-shelf algorithms, PPO, ATC, TD3, and so forth, can do rather well in managing it. Here is a not yet optimal algorithm where it tends to kind of overfish and is still yet most of the time keeping the stock around that optimal size here. And you can see that the rewards it's achieving are very close to what the rewards that you would have got under a constant escapement value would be. Great, we can manage simple fisheries problems that sort of look like classic control. What about more complicated problems like that tipping point example from the top? So in a tipping point ecosystem, you get very little information about your state because your state is kind of changing slowly in response to the sort of global forcing parameter. Think of this as temperature, mean temperature of the Earth. And over time, that's increasing. And you observe your ecosystem state only, and you see your state's maybe gotten a little bit worse. And all of a sudden, you hit this fold bifurcation, this catastrophe event, where you go this saddle branch, this sort of unstable point hits the stable point, and they annihilate. And you are forced over here onto the stable branch of the undesirable state. Now, as you may recall from the unequal systems theory, this kind of system, in order to get back, it has this property called hysteresis. If you go back to your temperature in 1990, say, you are no longer transported back to the favorable state. You are stuck here in the unfavorable state. That's a process known as hysteresis. You have to get all the way back here before you get another bifurcation event to get a sudden transition back up here. So this is a much harder environment to learn in because you get less signal, and a small error can lead to a very big and very difficult change to reverse. So how do we do managing those systems? So here's our global system with a bifurcation in it. And these are typical outcomes in which you apply just a standard conservation sort of maintain the steady state strategy. And we see lots of those involve transitions to the undesirable state. If I take the worst case outcomes of a training and reinforcement learning algorithm on the same problem, I see rather successfully that even when it does manage to tip into the undesirable state, it very quickly applies enough conservation effort to recover the system. And most of the time it can maintain the system away from that transition. I think I have some questions. I'll pause for a second, see if I haven't got too far ahead of the chat here. All right, looks like
so far have been me soliciting questions, so please
Great.
Go ahead for now.
Great.
Unless folks at this time have sort of things in the back of their mind and want to jump in now.
I'll keep going, but shout out as we go here. So I'm going to show you now taking all of those replicates instead of just 6 of them, but just average over here just to convince you that the reinforcement learning algorithm has indeed learned a strategy that on average keeps you into a good state, despite quite a large variance. It's clearly not yet optimal. It's outperforming this kind of conservation steady state strategy here. So this is sort of early work on tipping points, mostly led by one of my PhD students, Marcus here, and you can see this in his little preprint on the archive. So we can use reinforcement learning on these problems, but we're still only as good as the environments that we're training on. And so if the real world is quite different from these training environments, we could get dramatically different outcomes. So we still have a challenge of robustness that Schindler was suggesting to us, right? To say we need to go not across one plausible future and show we can do well, but across a range of plausible futures. And so in reinforcement learning speak, what we need is not a single learning example, but a curriculum learning in which our agent learns to perform over many different possible worlds. The nice thing about the RL paradigm is that it generalizes pretty nicely to this approach. And in fact, this has a lot of echoes of the scenario planning that we actually use to manage in the real world as well. That rather than try to make this is the most predictive model, this is the best thing to do, we try to come up with this is not a terrible thing to do, and it seems like it's not terrible under a variety of scenarios, so let's go with that. In order to do that, we need more gyms, And so one of the goals of this talk is to kind of encourage from the ecological side and conservation side, building up those possible scenarios. We're not very good at formulating our conservation problems more precisely into objective problems that you can start training a reinforcement learning agent on. And so by building gyms, we hope to kind of do some of that translation work. And we've started building out a collection of them that you can see here, inspired by the collection of benchmarks that we see as sort of so commonplace in computer science. So here's the OpenAI gym set, which focuses mostly on classic control, robotics, and games examples that have become standard benchmarks for reinforcement learning. So, does it work? As you may know, if you've ever tried to do anything with reinforcement learning, most of the time, it doesn't work. It's very hard. This isn't like our sort of mainstream machine learning, like supervised learning, doing classification problems. The ability to get these very glossy, fancy results that we saw at the covers of Nature and Science there has been restricted to some of the most elite teams in the world. And we try these sort of methods off the shelf. They can go wrong in many different ways. Just to highlight one of the many ways, there's a challenge of designing the reward in the first place. So sometimes you say, this is the objective of this management system, or this is the objective of my robot, and let's see, we'll train the system to come up with something. It can discover ways that you didn't intend to get out a large value. And so in this example, there's just a race car, which is supposed to follow the track going this way. You can see race around the track and get to the finish line as fast as possible, but it gets this small reward every time it picks up one of these little fuel containers here. So this was a popular Flash game before Flash disappeared, and training RL on it came up with this solution, which apparently beat all the other solutions. You can see our race car or race boat here is going in the wrong direction and has decided that the best thing to do is just kind of stay in this little spot where it can collect these little small rewards and actually never complete the course. And it will, you can see the score going up in the lower left there. In this sort of infinite loop, it gets a better and better score and never completes the objective that you actually had in mind. So choosing the wrong goal and allowing machine learning to go and figure out a way to get there, it may meet your objective in ways that you really didn't want it to meet it. That's only one of the ways you can go wrong, of course. I really like this example, that sometimes it will learn a solution and it can kind of get stuck going with that particular solution. So this is an example, again, of a robot that's learning to move. It simply gets a reward by moving to the right. And this example is a classic benchmark called half cheetah. And let's see how this particular algorithm decided to learn to do it. So here we go. Oops. And I love this. You could argue this is how we do conservation as well. Well, I've always done it this way and it works. And you don't explore enough into different strategies. So, this is moving me forward. I'm going to stick with this. And, maybe that's good enough. This is not a problem of reward design per se, but just our robot getting or our agent getting locked into a solution about what works rather than sort of better exploring a space where maybe it could learn to walk the way that it was intended to walk. In conservation, we have this similar challenge of a trade-off between exploitation and exploration. Do we try new strategies and try to learn something better, or do we stick with what already works? All right, thank you, robot. Okay, so at this point, I want to shift from the solutions we've been able to come up with so far and kind of the still open territory and being able to come up with more robust solutions in reinforcement learning or other ways to these ever-increasing problems, to zoom out a little bit farther and say, so will these algorithms do this, is what we've been focused on so far. Can they solve these problems? To will we regret it when they do? Before I begin this next session, I'll just pause again and see if I have any questions, and then I'll dive in here.
If others don't have immediate questions, I wanted to ask, when you're talking about uncertainty in these environmental setups, you're talking a lot about sort of uncertainty in the state, which is what motivates the use of POMPs, but then you're also talking about how we don't always know exactly what the reward function is and how to define that. So I just wanted to see if you, from your experience in this type of work, if there's a kind of component of uncertainty that you find to be more prevalent, or really throughout state, transitions, reward, everything?
Yeah, I think that the one we find that's the worst is always the one that you leave out, right? And so we start off by simply putting in uncertainty into the process, so all of the models are stochastic, right? And you discover, oh, the agents don't have too much trouble dealing with that stochasticity, just as Reid didn't, right? The partial observability is much harder for them, and for the exact same reasons that it's harder for the human beings, right? It means that the agent has to keep track of kind of everything that's happened, and it can't just forget history and kind of react to the most recent information. And so partial observability is hard. But just like again in the real world, the worst thing for the agents is this kind of the model uncertainty, is what you might consider a transfer learning example. So they work so well in the environment that you built with observation uncertainty, with stochasticity. You alter that environment in just a little bit. And in fact, the RL thing is particularly fragile to that. You simply like multiply the rewards by a scalar, something that should have absolutely no impact on like a classical algorithm. And it can't find the optimal solution at all. And so it can be very, very, anything that was fixed in its training thing, it can be weirdly specific to in ways that you wouldn't even expect coming from a classical optimization, and can really lead you astray. So there's this great sort of generalization power in concept there, also great power to kind of overfit in practice.
Yes, thank you. We also have a question from Benjamin Kellenberger saying you've introduced interesting works on RL, but also touched on curiosity-driven learning, for example, the robot learning to move. To Benjamin, these are two different areas. Do you see application potential of machine learning-based curiosity-driven learning to ecology?
Yeah, so there's just a whole host of paradigms to sort of say, how do I increase sort of exploration and get away from my half cheetah running upside down example, where it's saying I'm kind of stuck on a local optimum. Curiosity-driven learning, I'll sort of put as one of the things into that sort of bigger class, speaking loosely, right? This goes into as kind of hinting at sort of a much longer sort of parallel debate we have in conservation, right? In between, well, maybe I would learn something. Carl Walters has wrote about the importance of surprise in ecological management, that you really only learn something when you see something entirely unexpected. You learn that your model was wrong and you have to do a different model, or you learn something about so that you can decrease uncertainty about, say, the location of that tipping point. If you go to the best way to kind of manage a tipping point system, of course, is to kind of just walk to the edge and collapse the system and then go, oh, well, I should never do that again. But it's a very difficult environment to learn in if you only get one go at it. And so there's this trade-off between like, when can I learn? When is it safe to learn in simulation, say, and when is it not? When do I need to be sort of as risk averse as possible and actually manage the system? And so there is kind of a trade-off between when I'm training the system and when I'm sort of actually running the system in the real world. And it's a tension that we see in RL, it's a tension that we've seen in conservation as well, with just human agents instead of computer agents struggling with much the same challenges.
I think Kai has a question.
Yes, thank you for a great talk. I also have one question regarding previously you say good predictive accuracy might lead to wrong decision. So I think that also applies to the reinforcement learning setting where you might have a good model, the environment that you are interacting with, but that model might not lead to a good decision. So how do you think like the current reinforcement learning, how should we fix this issue?
Yes, great question, precisely, right? So I could have a simulator that I say, this simulator has been really validated against the real world. It's always made good predictions, right? And so therefore I only train my agent on that simulator. And then I find out that in fact, that simulator has made great predictions all the time while we're in, say, the good regime. And it just never saw a regime shift. And so it knows nothing about when that collapse happens, right? And I applied in a real world system with global forcing is moving us into unexperienced environmental conditions. Suddenly it's doing terrible, right? So how do we apply that? We do that in that kind of scenario planning, Schindler and Hilborn spirit, right? Of saying that I don't want to kind of focus on just the best, most realistic, best predictive simulations and train only on them, right? I really want to force our creativity to come up with as many possible scenarios and find strategies that are robust across those. Now we can do that in formal, when we have model-based control, we can do that in sort of formal terms, right? Where we say like, oh, I minimize regret or whatever. But the RL agents aren't doing that, right? They're just trying to learn heuristic rules that work across each of those environments. they never assign the probability that any of those environments are true. They don't try to learn about those things. So in fact, there's kind of take it a step further. One of the techniques we see within RL is adversarial learning. You propose environments specifically constructed to see if you can get the agent to kind of do something dumb, right? You say like, oh, you've always been trained here. What if the world were this? And that kind of adversarial design might help us as a concept in management as well to kind of develop more robust strategies to sort of what if scenarios.
Yeah, thank you.
I'm gonna take some more questions, but I'm gonna dive into the sort of second half here, and then we'll try to grab a couple questions at the end. So not just in RL, we're seeing algorithms play an increasing role in conservation across a broad swath of management and policy. I can divide these roughly into different groups. Methods designed to inform policy, stealing from the New York Times a couple of days ago. This map, we see lots of these expressed in terms of maps where biodiversity is most at risk. Algorithms that can identify individual species from camera traps, or even individuals within that species based on image analysis from those patterns. So these could ultimately be techniques that don't tell you what a policy is, but they might inform the policy based on kind of filtering and labeling of data. Examples like the RL case we just looked at actually try to select policies, right? So they do some kind of decision optimization problem, and it is not just trying to come up with some classification. The output of those algorithms is a policy, it's a decision saying, if you see this, this is the action the decision maker should take. We see those in non-sequential problems too, in saying, where should I prioritize conservation? What land should I purchase, for instance, to protect from development? And I can look at one of those hotspot biodiversity maps and allow the algorithm like Marxand to say, oh, this is the place where your conservation dollars would be most effective. And we can see that in a market sense as well. For instance, in pricing carbon markets in America's forests, as this company NCX is doing, being able to sort of look at total forest biomass, project how much carbon sink that can provide, and then put a price on that for companies that are trying to buy offsets. Lastly, you can see algorithms involved in enforcing policies from Forest Watch to Fish Watch, saying I can detect illegal foresting or illegal fishing, to maybe even this example of this RL-driven robot here, which destroys sea stars. So we do have killer robots already operating in the environment. I'm actually least worried about that example, but I'll talk about these different ways of which algorithms are playing a role in enforcement. So surely saving biodiversity is a good thing, right? And since we're just talking about biodiversity, yes, AI has these issues in human data where we worry about the ethics of the algorithms. But in these examples, our data doesn't have a human dimension, right? We're just looking at layers about biodiversity, layers about the environment. We don't have to worry about racial disparities, right? Like, we could all agree that just ending illegal practices of fishing or illegal foresting would be good for everyone. How could this go wrong? Well, first, of course, we have seen with algorithms in other contexts, they can have unexpected side consequences. For instance, this papers by Struble and Bender that got a lot of attention recently have highlighted the environmental impact that machine learning in particular has because of the extremely high energy costs. Now, as a percentage of the global environment energy costs, maybe these things are still small, and certainly not many of these cycles are dedicated to conservation algorithms so far anyway. But one thing that's sort of important about a sort of an unintended side effect. I'm worried about more dramatic side effects. Working within ecology it's forced me to sort of meet many different collaborators, including working most recently with political ecologists and sociologists. We started talking about sort of the role machine learning can play. And ecology has sort of made this mistake before, if you will, that there's a long history in political ecology looking at the ways in which conservation efforts, not necessarily driven by algorithms, have played out in very unexpected ways, in ways that we didn't intend, right? In particular, the best way to see some of these is looking at conservation practices in geographies of conflict. Unfortunately, many of the most biodiverse areas of our planet still are also areas of political instability. And this can play out in ways where conservation does not accomplish either the conservation task we want or the task of, in terms of human outcomes. So I'll take you first to Lanka in Myanmar, where separatists tried to replace the current military junta. And conservation has been co-opted by the junta to legitimize past forced displacements. Here, I'll just quote from the authors here because it's their expertise and not mine, of the Karen civilians by the Myanmar military during decades of war. impeding the potential return of refugees and internally displaced persons to their customary lands, which have since been zoned for the park. And the conservationists echo the sort of racialized discourses around Karen forest dwellers as criminals illegally foresting or living within protected forests, or as enemies of the current regime. And this ceasefire, on the flip side, has opened up places for sort of re-envisioning the allocation of that land, not merely from sort of a top-down approach of where the most biodiverse areas are, but this alternative model of a more community-led version of conservation-based indigenous rights. We see a similar story played in Sri Lanka. Here we have these sea cucumbers, which are protected species, but are allowed to be artisanally harvested by the ethnic population of there, which has been involved in a bloody civil war from 1983 to 2009, and ultimately suppressed by the majority ethnic population, in which this particular work by these authors have examined the role of marine protected areas, the conservation goal to allow the regrowth of both the sea cucumbers and the rest of the biodiversity there has been again exploited by the ethnic majority of the state as a way of preventing the continued harvests of the minority population, failing to achieve the conservation goals in building biodiversity by still welcoming in too much commercial fishing, while also the state is achieving its own security outcomes, which lead to these non-equitable distribution of resources within the different ethnic groups. Lastly, I'll take an example in Guatemala here, where we see surveillance technologies from satellites and drones, which have traditionally been a source to facilitate containment of these sort of risky populations and produce new kinds of borders. However, in this example, the authors point to the way in which drone technology and satellite technology is able to as well be used sort of in reverse. In political ecology, Peloso has coined this term for mapping as a resistance act, as well as the maps can lead to dispossession of land, but they can also be a way of counter mapping, sort of fighting back in the technical space, saying, no, we are going to assert our own control over these areas by sort of using bottom-up approaches to do their own sort of mapping of where these resources are. So a quick walkthrough of those examples. We can draw many more, highlight a couple sort of large-scale points from environmental sociology and political ecology that are worth keeping in mind as we think of applying conservation objectives to actual outcomes around the real world. Is that first, we can never separate the sort of the human and non-human natures. The human interactions with the environment are what got us into these problems in the first place, but the human interactions are always part of those environments, and we can't address challenges in biodiversity without thinking of those dimensions. And in particular, paying attention to the role of both power and social inequality can play in shaping those interactions. And so we can sometimes achieve conservation goals while also increasing inequality, as we saw in some of those examples. And sometimes we, in fact, fail to achieve either the conservation goal or the goal of addressing instability or social inequality. Okay, but what does this have to do with the data, right? If conservation is going astray, and as those examples were not technologically driven, those are kind of historical mistakes that conservation has faced by kind of parachuting in the past with a biodiversity only view and not taking into account the appropriate sort of human and political contexts of the area in the way that those policies would be realized. But is the data at fault? We think of data-driven environmental governance, where data is neutral. This is sort of objective resource for which we can make accountable and transparent decision makings around nature. That these data-driven approaches are better, right, than rather than not. So I'm using language here from Goldstein and Nonst that examine the role in which basically all of these things are not really true. And we already know this as scientists, right, that there are sort of our data can contain biases and are only able to express what's already contained in our algorithms. Let's grab a couple of examples. So just one more piece from Goldstein and Nonst here. Contrary to the kind of rhetoric that we use, data is not a free-floating in the world, patiently waiting for conservationists, governments, and corporations to come along and plug into environmental management, but instead data is infrastructure, a word that we're very familiar with, right? That it's connected to specific funding, developed for a specific purpose, tied to particular standards, rules, technologies, and environments. That ultimately, all of that context influence how what outcomes we do and do not get from that data. So these are questions, in other words, not only of ethics, but of power. So we took one look at this in talking to colleagues in sociology that introduced us to the language of Stephen Luke's, the faces of power, that we can't just focus on who is making the decision, but what data we have influences what agenda the decision will consider. You can think of in RL terms what the possible structures of reward functions are, and even defining what the terms of the discussion are. We call this, borrowing from Luke's, world-making power. That's sort of what are those possible environments. We can't consider scenarios that we can't express. And so the role of algorithms in defining these does have a recognized impact on the outcomes. You can't just sort of hide behind the decision maker saying that, we're not responsible for these outcomes. We explored these concepts in a paper with to NeurIPS, our first interaction with individuals looking at political economy of reinforcement learning systems in other contexts where they're used, for instance, in self-driving cars, and where we can start learning some of the similar mistakes and opportunities from them. And one of the advantages of having social scientists on your team is that when you apply to a conference that uses this image as its cover, someone can immediately tell you that that's indeed Hobbes's 1651 Leviathan there, and explain the political significance of the monarch. And if you take a look at Hobbes in a reinforcement learning sense, you think like there's quite strong opinions about what utility functions actually are and the way you should and shouldn't use them. So we can learn a lot from our social science colleagues there. Just a couple more examples here, that even when the algorithms can be fair, if the data are biased, we can get undesirable outcomes. So this is in the UN Law of the Sea discussions that are in their fourth and final round. Based on introducing algorithms to make more fair outcomes, most of the historical data comes from countries that have developed fishing at an industry level, industrialized fishing, and the data from countries in which there's just more artisanal and indigenous fishing are just absent from the data sets. And so the historical catch reflects countries' industrial exploitation rates and underestimates the allocation that would have gone to these more indigenous and artisanal fishing communities. So because the data is not representative, even if the algorithm is good, the outcome is not necessarily fair. And it's not necessarily a value one way or the other. It's just sort of introducing the complexity of the space. This term from Fairhead et al. Of green grabbing. We see that when we're interacting with the environment, green grabbing builds on this well-known history of both colonial and neo-colonial resource alienation in the name of the environment, whether for parks, forest reserves, or to halt the assumed destructive or local practice. It involves novel forms of valuation, commodification, and markets of pieces of nature, an extraordinary range of new actors and alliances, from pension funds to venture capitalists, commodity traders to consultants, GIS service providers, ecosystem companies, military, green activists, and anxious consumers, all finding, among others, a once unlikely common interest. Now, this isn't to say that this practice is good or bad, but to highlight the sociology and the political ecology depth of these questions, that we have very many new actors involved in these processes with some shared objectives and some competing objectives, and changing the way in which we define utility functions, this valuation in terms of market terms, in terms of the different utility derived by the different groups, that just highlights the potential for very complex outcomes. So to sort of summarize here, we've seen ethical questions, that there's just, is the overall outcome distributionally equitable? So within our examples of conservation going awry in the MPAs in Sri Lanka, for instance, that we see different ethnic groups getting very different outcomes. Or is there procedural equity in the design of the sort of UN Law of the Sea? If countries are not represented in the process, do they have rather than in the outcome? And these raises political questions as well. So they're not just questions of whether the outcomes are good or bad ethically, but are they legitimate? Which actors have the rights or the role to say, this is the law or this is the action that we take? And if we talk about legitimacy from the standpoint of an individual sovereign nation making rules versus another country versus a technology company within another country, sort of impacting the outcomes worldwide. And then the question of accountability. So if you change the results and you're successful in achieving conservation goals, but unsuccessful in the equitability space, is there an ability to be accountable for those decisions? So there's a broad set of questions to face in there. And I think that they echo the kind of overall pattern here that we saw within the beginning. The first half of the talk, we saw how optimal solutions oversimplifying uncertainty can easily lead us astray. And instead, we can search for just more approximate solutions that can get closer and closer to reality, get more and more reality in there in this kind of scenario approach. I think this is essentially the same lesson that we are pointing at in addressing these human dimensions. So not only can we not just kind of zoom into some of the complexity of the ecological system, but there is an inseparable social system, which if we're leaving out of our model, we're leaving that context out of our model, we're also going to be optimizing the wrong problem. And in order to do that correctly, we will need this much broader collaboration, not only between environmental scientists and engineers, natural scientists, but also sociology, political science, economics, law, and ethics. All right, I'm just about at the top of the hour, so I'll stop there. I think a large team, particularly my PhD students, Marcus has led most of our reinforcement learning work, and Millie has led most of our work in algorithmic conservation and the political science context there. And I think we'll have a little bit time to take any questions.
Thanks so much, Carl. Before we move to questions, I just want to give a thank you to, now there's an audience in the room, but then also from our virtual audience as well. Okay, and with that, so there's a question in the chat about what are the steps we need to take to avoid the unintended consequences of algorithm design and implementation. What can we learn from nature? Taufeeq Ashiru asked this.
Yeah, great question. I think the first step is just acknowledging that those unintended consequences are possible. If to do that, I think we can turn to some of the literature coming from these other fields, examining what it means to do good through algorithms. One of the advice we found in political ecology is an emphasis on embedding someone with expertise in that particular context as part of the team, right? Now, what does that mean as far as how do you sort of translate and avoid those decisions? I think there's a huge space that we need to answer there. Some of those might be saying, oh, you've simply left out, the human component from your utility function, so that needs to be present. Some of those might point to deeper problems that are harder to kind of put into the algorithm, right? And so we can't always embody them with technology, but I think building that partnership is the first step to be able to kind of identify, it's not the things that we've modeled that are going to get us, it's the things that we've left out. And without that expertise on the ground of knowing what all of those are, we'll miss that. I think there's also a notion of like when you're in one particular field, like it's easy for all of the other fields to seem like they're one, right? So it's not just enough to have like a partner organization or a partner project that has expertise on, say, the ecological elements, right? And say, now they're responsible for everything. We need to have, make sure that our team represents kind of the broadest expertise possible that can understand the human and social context in which we're operating and not just the ecological context.
Wonderful. Oh, so we are at the top of, just about at the top of the hour. I know that there are a number of folks scheduled to chat with Carl individually later this afternoon. Thank you again for taking the time to do so. Perhaps for those who still have questions, Carl, if you are able to stay on for a little bit before then. But I also know that Milind Tambe, director of CRCS, wanted to say a little bit because he is in India right now and had to join a bit late.
Carl, I was able to, yeah, can you hear me?
Yes.
Yes.
So Carl, I just wanted to say thank you. I joined a little late, but I was able to hear most of the presentation. Wonderful presentation, lots of lessons learned, lots of possible overlap. We would love to discuss more just from a selfish perspective in terms of possible avenues for collaboration, but lots of topics right from the very beginning when you discuss this idea of best prediction doesn't necessarily lead to best decision. So highest accuracy prediction versus highest quality decision, there may be a mismatch. to all the way at the end when you discussed building these interdisciplinary teams and the potential for harm that can come from use of ML and AI models in conservation, which we would love to explore more. So thank you. Really very wonderful talk. Really appreciate it.
Yeah, thank you very much. And I'm right there with you on collaboration. As you can see there, I'm still becoming more conversant with so many of these dimensions, and I've learned so much from other collaborators. I think that's really what we need to move forward on these tough questions.
Wonderful. Thank you.
So for those who need to pop off, now that we're at the end of the hour, we welcome you to do so. Otherwise, Carl, maybe we can just circle through the questions that are still remaining. So there was one that was in the audience, the physical audience here with Arina Tokova.
Hello. Yeah, thank you for the talk. I was curious for the first section about so kind of trying to understand what the deployment would look like. So from my understanding, kind of apart from setting the limits and setting a policy for fisheries management, there would also be kind of the human aspect of compliance. And I was curious if there was kind of an outlook on how to either factor that into the model, or how different policies would kind of could potentially affect compliance. Like if,
yeah, that's a great question. Yeah, so first, right, so with fisheries, for instance, currently without the algorithm, human managers come up and say, this will be the allowable catch, 10 metric tons, right? And they will enforce that by saying that we will have an agent on the docks or even on the ship, the fishing vessel itself, and we're basically monitoring how much you can harvest, right? And you can imagine many ways in which, for instance, those roles of that human agent could be automated by a robotic agent, and questions that may or may not raise in the process of doing that, right? But right, as you then allude to, it opens up more possibilities. For instance, if you look into the data, if you say, for instance, in tuna, the allowable catch is consistently below the actually delivered catch, right? So you could imagine then that your agent needs to kind of learn that there's a mismatch between what is regulated and what manifests. And you say, oh, well, maybe I need to kind of adjust the regulation to anticipate that there's going to be the overcatch, right? Or maybe I need stronger enforcement to decrease the distance between the target and the observed harvest. So many different ways that could go. To highlight the ethical questions that involved in this, you can also see this as a transition between that enforcement has typically been sort of left up to the legitimacy of the government, right? So that there is a federal elected agency which is responsible for doing these things. And of course, it can be very politically unpopular to shut down a fishery, and it is responsible to political pressure. But it is also accountable to the human and economic interests in the area about the decisions they make, right? And we're in a very different world when that decision-making power is moved from the public sphere into, or mostly into, an opaque algorithm that may not be being executed in the public sphere, but is being done by some company. Now, I'm not trying to put a particular value that's necessarily good or bad. It could be both, but it's certainly a complex change that's worth us thinking through.
Thank you.
We also had a question that just came in from David Grossoff. So David asked, is there any value to achieving robustness and avoiding tipping points by using models of coalition politics of parties? Parties are recommending policies based on diverse models and data. In other words, can robust political process fix the other uncertainties?
Yes, so I think that's really interesting. And I think at the end of the day, the answer is probably going to vary. There are no doubt cases where we are able to discover a robust policy, right, that can say, look, under these conditions, you can at least always avoid the tipping point, right? You may not get the maximum economic value out of the system, but you'll be robust to avoid sort of this worst case outcome. But there are going to be complex systems in which there is sort of no sort of guaranteed safe path, right? That we just don't know enough about the underlying dynamics to know whether we can avoid it or not, right? And in this case, this is what one of my colleagues refers to the difference between sort of a technocratic and democratic way of making decisions. That if we are all going to bear the costs what's perhaps most important is that we all feel that we have buy-in to the process, right? And that it is not only sort of one, since there isn't a right answer that we can determine ahead of time. Well, we all agree that like, well, this is our best guess, and then we all are somewhat accountable for whether that outcome turns out well or not. And I think we can indeed learn, as your question hints, right? So that there, instead of doing this kind of single objective optimization, we can imagine, and we can do this within RL as well, right? Having multiple agents that are sort of competing with different policies and different objectives. And we can examine sort of what are some of the outcomes that might result from those kind of dynamics rather than sort of the single global optimum utility.
Wonderful. Thank you so much for staying a little bit longer to address these last burning questions. Maybe we'll end it here, but I know that I think 5 people are